the mission continues.
Okay. All right, thanks. In fact, the speakers yesterday already mentioned many of the things I'm going to talk about today also. That doesn't deter me from going back and telling you the basics of some of these topics. It's a little difficult to kind of fit in and kind of give you a good overview of things that would take a whole semester-long course to do. So I'm not even calling this the outline of the talk. These are the kind of keywords that you'll see in the talk. I'll try to, give you some useful information, but clearly, there's more than that fit in a talk. So I'd spend a lot of time on secure multi-party computation, but more basic things than what Kermit was talking about yesterday. So things like linear secret sharing. She was going from passively secure protocols to active security. So I'll actually tell you about the passive secure protocol. And there are many more other simple basic things I would have liked to talk about today, but we don't have time for that. So I'll omit things like Yavuz garbled circuits and a generalization of that by Yuval and Al called randomized encoding, which is a very basic idea. And then somewhat more esoteric things like conditional disclosure of secrets or composition issues. Universal compositions. So I will omit those things. I will talk a little bit about private information retrieval, but again, in no great detail. Oblivious RAM, searchable encryption, just one slide mentioning all these three things. Okay, and a few slides on homomorphic encryption and fully homomorphic encryption, and also drop in names of a few other cryptographic tools. I'm saying they're out there in the horizon. They're not quite in a form that you could use in practice, at least not the most general notions of these things. So in practice, you would just use hardware for these kind of things. But I think it's also not particularly secure. But okay, so let me start with secure multi-party computation. A special case of secure multi-party computation, which is what you would often come across, is called secure function evaluation. So the idea is that there are a bunch of parties who have their inputs, and they would like to compute some function on their joined inputs. Maybe the function gives different inputs to the different parties. And so to compute a function of private inputs without revealing any information other than the output to each other. Okay. So reveal nothing beyond what's revealed by the function. I'm not going to give you a formal definition. I would like to, but it would take a few slides, couple of slides to do that. But I want to kind of mention one more thing here. Beyond secure function evaluation, MPC also talks about functionalities which are reactive or interactive. So a very classic example is a poker. So a bunch of parties want to play a poker, but there is, or some card game, there is no trusted dealer. So then, can you carry out a game without a trusted dealer? What you need to ensure are a bunch of things, right? The cards need to be shuffled and dealt correctly. So everybody, no card should be dealt to the same party. It should be randomly picked. So correctness and, it should be random. And it should be secret. Nobody else should know my hand other than what they can infer from their hand. So it's complete secrecy. And not just dealing, right? After the cards are dealt, we're going to play. So when I play a card, everyone should be convinced that I didn't make it up. It is actually a card I had in my hand. So that needs to be done throughout the game. Okay, so that's as if I had a trusted party with some memory sitting there, mediating this entire game. But secure multi-party computation is what we are asking for is to be able to do that, to get that effect without having a trusted third party or trusted party. Okay, so without a trusted party. So in fact, poker was incidentally one of the old, starting points, maybe the starting point of secure multi-party computation way before even, we had formal definitions of security for things like encryption. Okay, so this Abstract is probably a little too, tongue-in-cheek. There was no formal definitions, or not in the form of security we have now. But this is a paper by the same people as RSA, Shamir, West, and Edelman, putting out this problem of, can you deal cards and then play those cards without having a trusted dealer? Okay.
The company called SRA.
Yeah. Yeah, so probably today, unfortunately they didn't do that, and MPC still remains much more obscure compared to public key encryption. So maybe blockchains is now what will change that. MPC is getting more exposure thanks to the blockchain companies. Okay, so just one more, summarizing what MPC is, again, staying informal. I don't have time to actually do anything, give a formal definition. So the goal of MPC, as opposed to cryptography that you traditionally see, is instead of emulating a secure channel, we are emulating a trusted computer, okay, or a trusted third party. And here, trusted means you can send your inputs to that party and be reassured that the trusted party is not going to leak your inputs beyond what its functionality demands it to do. So its functionality will say, take all these, say if it's an auction, you all send your bids, and it might publish the winning bid, right? That's its functionality, that will do, but it won't reveal anything else. So your bid, if it didn't make it, wouldn't be revealed. And it can be trusted not to cheat. Okay, so trusting is one, not to cheat, and the other, not to reveal information. Okay, they're all essentially one package deal. And yeah, so this is an important tool for mutually distrusting parties to collaborate. Okay, so before getting into anything technical, since a lot of the discussion is about practical implementations out there, you could ask, is MPC actually something realistic, practical, or is it just something theoreticians have been working on since late 70s and when that mental poker came out? Well, things have been moving along. There are many implementations, starting with some very simple attempts to implement, all the way to pretty realistic implementations. And there's a web page that tracks, that lists a lot of MPC software, and it is really a lot of MPC software there. So, and it's not just academic research. There is some commercial implementations also. Ivan Damgard and others, started this, they had a paper originally on beat-sure auction, and I believe, from all that, this company in Denmark called Patricia, which has been doing a lot of real-life deployments according to their webpage, so you can go and see their examples. Yeah, so things like sugar beet auction, where it started, and electricity auction, spectrum auction. So a lot of very high, stakes computation, right? A lot of money being trusted on this technology. There are prototypes in the banking sector. There are proposals which may or may not actually get implemented. In Estonia, for instance, for tax, proposal for satellite collision analysis. So all the countries have their satellites, they know where their satellites are. They don't want to reveal where their satellites are to all the other countries, but all of them would like to make sure their satellites are not at the same place at the same time. You don't want to have collisions. So can you just figure out if some collision is going to happen or not without revealing anything more? So that's an instance of needing to emulate a trusted third party. And last year, there has been some proposed legislation in the US, and the last I checked, this bill is still alive and could become a law. to use MPC for a real-life application. What they had in mind is some higher education data system where the students can make queries about the university's placement history and so forth. But they wanted certain kind of secrecy. The law, instead of saying things should be secret, actually says you should use secure multi-party computation as part of the law that has been proposed. So it's getting more and more realistic over the years. Now, MPC is a big literature. There are several dimensions of the problem. It's not a single thing. We saw a few things that Karmit was talking about yesterday: active security, passive security, honest majority, not having an honest majority, so the corruption threshold. But there are several other issues, and it keeps cryptographers busy, I guess, but it's not something I'll actually get into in this talk. Okay, so now actually to something a little more technical, and I'm going to start with something simpler than MPC. Maybe in the context of real-life applications, this is probably much more impactful or easy to use than a full-fledged MPC. This is already, it's a very simple idea, you'll see, and it's already something powerful and not as exploited as it should be. Okay, so that's secret sharing. So what's secret sharing? So there is some dealer who has a secret, some message, and she encodes it into, so there are n parties, and she encodes the secret into n messages, one for each party. Okay, so these messages are called shares. And the deal is that a few of these parties, say a party gets a share by himself or herself, that party has no idea what's in the what the actual secret is, what the actual message is. Okay? But if a few of them get together, they may be allowed to figure out the message. Okay? So a subset is called privileged. I'm calling it privileged if they are allowed to reconstruct the message. So privileged subset of parties should be able to reconstruct the secret. And on the other hand, a subset of parties come together, they are not privileged, then what their shares should have no information about the actual secret. Okay, so what they have is essentially just some random strings should be distributed independent of the secret. Okay, and as I was saying, it's very useful. You can directly use this, for say keeping your data in multiple servers who you hope don't collude with each other. And this makes sure that no party will get, no server will have your data by itself. And in fact, keys, so DNS root keys are secret shared. So this is an actual application that's used, that's really done in the network security that we are all relying on today. But it's also an important component in other cryptographic constructions, in particular MPC. But also other kinds of fancier kind of functional attribute-based encryption, for instance, or if you want to build something that's leakage resilient, which is something cryptographers have been looking into more recently, and these all use secret sharing as a basic component. Okay, there are different kinds of secret sharing, but I'll mostly talk about this thing called threshold secret sharing. So NT secret sharing. So N is the number of parties to whom you are distributing your secret. T is a threshold. So the idea is that, so the shares, there are N shares. If you take any T of these shares, T or more of these shares, that will let you reconstruct the message, the secret. But up to T minus 1 shares do not reconstruct the message. So in this case, the privileged sets are sets that have at least T people in it. And if you have fewer than T people, then you should have no idea what the information is. Okay. So should have no information means if you look at, say, first T minus 1 shares or any subset of T minus 1 shares, that distribution stays the same for all messages in the message space. So we don't need to assume a prior on the messages or anything. There's a robust way to define that the view of this unprivileged set has no information about the message. Okay, the simplest setting is 2 out of 2 or 2-2 secret sharing. So you have to give shares to 2 parties, and only if both of them get together are they privileged, should they get the secret. Here's a very intuitive way of doing that. You would say, okay, I'll take my message and I will encrypt it with a key, right? So symmetric key encryption. So I pick a key, I encrypt my message, and I get a ciphertext. And to one party I give the key, to the other party I give the ciphertext. And that's a very reasonable 2 out of 2 secret sharing. Just holding the key gives you obviously no information about the secret. Just holding the ciphertext without knowing the key gives you no information about the message either because of the security of the encryption scheme. Okay. So that is a very reasonable secret sharing scheme, except it relies on the encryption scheme being secure. But that's not a big deal. We just need this encryption scheme to be secure as a one-time encryption scheme, in the sense that each time the dealer is going to make a share, she can pick a new key, right? That's going to be one party's share. So in that case, you don't need any computational assumption. Your encryption scheme can be what's called the one-time pad. So one share, the key is a bit string which is as long as the message, and then ciphertext is just a message XORed with the key. Okay? So this is a very symmetric scheme now. There are 2 shares, both of them by itself. Each of them is a random bit string. You XOR them together, you get the message. Okay. You can go generalize this. This was 2-2. It directly generalizes to n secret sharing. And I talked about bit strings, but the bit strings are a special case of a finite group with, finite, or if you don't know or don't want to think of finite groups, you can keep thinking of bit strings. And when I say add 2 bit strings, what I really mean is XOR them bitwise. But it works for any finite group. The messages come from a finite group, and the shared space is the same group. And to share the message, here is one way to describe it. The first n-1 shares you pick uniformly randomly from the group. Okay? And the last share, you set it up such that if you were to add all the n shares together, you'll get the message back. And if you're paying attention, and I've written it in this way, the group doesn't have to be commutative group. It can be any finite group. But if you're thinking of bit strings, it doesn't matter. Okay? So you XOR all the bit strings together, you'll get the message back. But each bit string or each share, or in fact, n-1 shares by itself is uniformly random. At least the first n-1 shares, by the way I described it, it's clear it's uniformly random. But this scheme is actually very symmetric. You could have thought of you could have taken any n-1 bit strings, they're uniformly random. Okay, any n-1 shares. And the reconstruction is just by adding up all the shares. So it's called the additive secret sharing because the reconstruction is by adding up all the shares. And it already gives you a useful computation protocol for secure computation. So here you do need the group to be commutative, so you can think of them as bit strings now if you want. Okay, so here's a goal. Here's my task, and I'll tell you the protocol also. So there are n parties or some number of parties with inputs. Each party's input is an element from the group, so say a bit string. Actually, maybe here bit string is not the most useful thing, right? Think of them as numbers. So we want to add up our salaries or something, okay? So, and we know some of our salaries is not going to be larger than $1 billion, hopefully. I don't know if there are any billionaires here, but certainly salaries cannot be billion in India. You want to just, so you work with integers, but work modulo a very large number. We are now going to overflow that upper bound. So that could be a finite group, working modulo integers. And the output party wants to learn the sum of these inputs with the different parties, but they don't want to reveal anything other than the sum, right? And let me describe it as, these parties are assisted by some servers. They're not trusted servers, right? So we would like to emulate a trusted server, right? They all send it to one server who does a summation, gives it to the client. We don't have a trusted server, so instead we are going to use secure multi-party computation to make these servers do the job for us. And it's okay as long as all these servers don't pollute. Okay? That's our, okay. So here is a protocol. Each party takes its message, its secret, its input, and additively shares it among all the servers. And everyone does that. And let's look at the first server. What the first server gets, it gets one share from each of these parties. What does it do? It does something crazy. So these are all kind of random elements in the group, right? If you look at one share, if you look at n minus 1 shares, so n is 3 here. So if you look at even 2 shares together, it's a random element in the group. So it seems like totally pointless for the server to do anything with the things it gets, right? It's got random elements. But it goes ahead and does the summation, okay? As if it's doing this job, It does the summation and sends the sum to the client. And everyone does that, okay? Okay, so the client gets a bunch of random numbers, which shouldn't mean anything, except the client goes ahead and adds all of them together. And if, sure enough, that would be the, that would be the correct value. So here's what happened, right? Each party took its value and wrote it as a bunch of shares. So 3 shares rather. So in this case, 3 shares. And each of those 5 parties did that, right? So they rewrote their value as, so these 3 things add up to this value, okay? So we have a matrix of these shares. Each secret is shared as this row. And what does server 1 get? It gets the first share from all the input parties. So it got a column. And it went ahead and added up this column. So it got some value. Second server got, the second column. The third server got this third column. And they send the sums of these columns, so these 3 values, to the output client who added it up. What did we want? We wanted the sum of these values. But sum of these values is the same as sum of this entire matrix, right? Because each row gives you sum of one value. And some of these values is also same as the sum of the entire elements in this matrix. It's just that we did it in a different order, all right? So indeed this is correct. What the client will get is the right value. And what does the client learn other than, so it learns actual sum. What does it learn other than this? Who knows, maybe, some crazy combinations have been given to you. Maybe you learned something else. Well, you can show that actually no. The client doesn't learn anything other than the total sum. But it's even better, even if the client colluded with 2 of these servers. Sorry. If the client, of course, colludes with 2 of the servers, it still learns the sum. If, say, 2 of the servers collude just among themselves, they learn nothing, absolutely nothing. They don't learn the sum or anything. If the client colludes with 2 of the servers, it will still learn the sum, but it will not learn individual parties' values. Okay. So this is a very good protocol. It's secure only against passive corruption, though. Any one server can easily change the output by reporting something wrong here. But for what it does, it's a very simple protocol. Okay, so this I'm working on a group, so the only useful thing you can do is add. Group has only one operation, but if you're working on say a vector space or say a ring or something where it means it makes some sense to have a linear combination. So you don't just add them, you do some weighted adding. Okay? Then we can just have these servers do the weighted addition, and still the client will learn the correct linear combination, nothing else. Okay? I'll say a little more about this shortly. Actually, so why, what I just now said, more, formally what's going on is that there was a nice linearity property for this secret sharing scheme. Okay, it was very simple, additive secret sharing, but let me write it. So this was a secret sharing scheme. Let me write it slightly differently using matrices. Okay, so here is what the secret sharing scheme did. The dealer had the message, and she picked n-1 random group elements. Okay? They happen to be the first n-1 shares, but you could think of this, deriving the first n-1 shares as multiplying this column, this vector, by rows like this. So this is basically the identity matrix. I put it slightly to one side. So if you multiply this vector and this vector, you get S1. This vector and this vector gives you S2, and so forth. So those are the S1 to S2, up to Sn-1. And what is the last Sn is just M minus S1 plus S2 plus Sn-1. So now onwards, everything is commutative. And we are in a, so multiplying wouldn't make sense in a group. Here it would, because you are just doing multiplication by 0 or 1, which is to say take the value and keep it as part of your summation or not. Okay, multiplication by -1 means take its negative and then add. So that's what this secret sharing scheme was doing. It took the message, made a vector with a bunch of random elements combined with it, and multiplied it with a very particular matrix. Okay, and whatever came out were given out as the n shares. Okay, so that is the structure of this secret sharing scheme. And to reconstruct, what did we do? What did we do? We get the shares. We said add them up, which is to say take a multiply it with this all ones vector. And if you look at this multiplication happening on the other side, what you would see is that, so this was all ones vector. This was a matrix we had here. And if you do this multiplication, it comes out to the first element would be 1. So I'm just multiplying these two things. So it'll be 1, and here it's a 1 and a -1 add up to 0, and here also 1 and -1 adds up to 0, and so forth. So this product is the vector 1, 0, 0, 0. And sure enough, if you multiplied 1, 0, 0, 0 with this vector, you would get the message, right? Which is what the reconstruction was doing. Okay? So I just made something which is very simple, sound more complicated by saying, look, what happened was the sharing was by multiplying the secret and a bunch of random elements with a matrix, and reconstruction was by multiplying it with a very special vector. Okay? And the property of the vector was that when you multiplied this R and W, you get the vector 1, 0, 0, 0. Okay? That will guarantee that you will reconstruct it correctly. Now, from here to go to NT secret sharing, let's try to do exactly the same thing. What would we like to be able to do? Well, in NN secret sharing, you are, to do the reconstruction, all n shares were available to you. So I could do some multiplication like this. With NT secret sharing, you have some subset of shares. So I cannot ask you to do a linear combination of all of them. Okay, so instead I'll ask you to do a linear combination which only uses the subset of shares you have. Okay, so let's say the subset of shares you have is T. T is here subset of the set 1 to n. And it has at least T elements. Say it has exactly T for simplicity. And what we are looking for is a vector R for that subset T, such that RT times the secrets would give you the actual message. With the RT times the shares will give you the actual message. and RT has non-zero values only in positions which are in T. Okay? Which is the same as saying what I'm looking for is RT times W should be this 1000. Okay, so I'm looking for RT times W to be 1000. So that this will work for all messages and randomness. And if I could do that, I didn't tell you how to do that yet. But suppose for a second we can do that. We can find some W, we can find RTs. If we can do that, that's actually going to be a secret sharing scheme already. And the secrecy part, so the correctness is what we ensured by saying RT times W is 1000. The secrecy part is kind of automatic from this being a linear scheme. So there are two possibilities, right? Either you are privileged, in which case there exists an RT such that RT times W is 100. You meaning the subset T is privileged. In which case, of course, you are allowed to learn the secret. But suppose the subset is not privileged, which means restricted to, maybe I'll draw that here. So this is your entire W. Let's say, this is the positions indexed by T, okay? And there is no R such that RT times W is 1000 and RT only has support here. So you can ignore this part, right? What I'm saying is that there is no vector RT, this part is all 0. There's no vector RT such that RT times, let's call it this WT, is equal to 1000. It's not possible, which means 1000 is not in the span of these rows. So you can basically add for any possible message. I can add another equation saying so 1000 times the message. Sorry, maybe I shouldn't. Okay, or basically what this means is that I can add an equation saying the 100 times, so equation where maybe I should say what the variables are. These are my variables, right? The message and the various randomnesses that are used. Think of them as variables. And as somebody who's trying to find out about the message, you're trying to solve this equation, well, at least solve the system, at least for this variable m. Now, the 100 not being in the span of the equations you received, the rows you received, means that I can add an equation saying 1000 times this vector is equal to m. I can add that equation for any m of my choice, and it'll be still a system with a solution. I won't have any conflict there. And then I can solve for it. And when I solve for it, or I can ask what is the solution space, I get some subspace of randomness for which the solution, this holds. Okay, now the point I was trying to make is that from linearity or from linear algebra, the number of solutions just depends on the rank of this matrix. Okay? So there was some matrix to which I added 100, one more row. It had nothing to do with the actual message. So for every message, the number of solutions, just number of solutions meaning number of possible randomnesses that would explain the shares you got as having come from the shares of this message is the same number. Okay? So that translates to saying the probability, maybe I have a line for that. Sorry, I don't have it. That means the probability of getting the particular shares you got is the same irrespective of which message was used for secret sharing. Because the number of ways in which the shares you got could have been generated is the same no matter what message was being used. Okay, so that is the secrecy part. I didn't formally define secrecy, but that's what it is. Okay, so the if you got lost in some of the things I was trying to write there, doesn't matter. The bottom line is that if I could just set up that only my privileged sets T will have an RT of this type and others don't, then I would have a secret sharing scheme. And sure enough, there is a way to do that. That W, So it's what's called the one-to-one matrix. But instead of saying it this way, maybe a more familiar way, you describe the secret sharing scheme. So it's called the Shamir Secret-Sharing scheme. Let's just say you pick coefficients of a polynomial, a degree t polynomial, degree t minus 1 polynomial, set the constant coefficient to be the message itself. The other coefficients are random. And the shares S1 to Sn are obtained by evaluating this polynomial on a bunch of non-zero positions A1 to An. Evaluating this polynomial in, say, at A1 is the same as taking the dot product of this with this vector. Right? That's why it's evaluating the polynomial. So the shares are FA1 up to FAN, and the secret is F0. How do you reconstruct? For any given subset T, which is more than little t, greater than or equal to little t size, there is a vector. What does that vector correspond to? That vector corresponds to polynomial interpolation. In fact, you can solve for all the coefficients if you wanted. In particular, you can solve for the first coefficient. That's the thing we are interested in, the interpolation that we are interested in. So you are computing F0. Okay. Any questions? Okay. All right. So I hope Karmit assumed this and much more, but hopefully this is useful. Now, if you know how to share one secret, sure enough, you can share any number of secrets. Just keep using fresh randomness every time. But it's the same procedure, so same W. And so so if I have a vector of secrets here, I have a vector of shares here, right? So each party gets one row in that matrix. And now, suppose I have shares, the parties have shares of, say, some 3 secrets, and they want to find shares of a linear combination of these secrets. That's easy enough because matrix multiplication is associative. So I'm interested in coming up with a secret sharing, so W times, not M1, M2, and so forth, but some linear combination of them. So some element M1, M2, MV times Q. That's the metric. That's the message I'm interested in, right? So I want to use this Q to linearly combine my secrets M1 to MV. Well, I can now, if I were to do that, maybe I have no, I don't. What I would have really done is I would have done this multiplication first. I got a single element, I pad it with a bunch of random strings, and then I apply W. Instead, what I've done, I didn't do that. I didn't know of this Q ahead of time, so I secret shared this with you. But now you can go ahead and do this yourself. Each party can take their secrets, linearly combine it using this Q, and get a single element. And that is a valid share in a valid sharing of the original secret. Okay? Not using independent randomness. The randomness is determined by the randomness here, but that's not a problem. So this is something we can do without communicating with each other. So they don't learn anything more than what they knew before, which is nothing if they, if less than T parties come together. So they can now, they can continue to know nothing about the actual secret, but now they can hold a sharing of some linear combination of the messages. Okay? And this is a very useful, this is by itself useful, right? You could already, you don't know what kind of linear combination will be needed later, but you go ahead and share things now. Later, when Q appears, you ask people to get the sharing for the linear combination, and then maybe they'll reconstruct that. So you can reconstruct some linear combination of the messages without reconstructing the messages at this point. And this is a useful, this is a useful little subroutine in secure multi-party computation. But let me describe it still in terms of secret sharing. So suppose I have two linear secret sharing schemes. Okay? We already saw two. One was an additive secret sharing, another was Shamir Secret-Sharing. They are different secret sharing schemes. So you want to go from one to the other, or some other two linear secret sharing. So W and Z are the two matrices I'm interested in. They both have their own reconstruction vectors. Okay, so suppose you're given shares in according to W of some message M. Okay, so this was our picture from before. The shares are W1 to Wn. Party I holds Wi. Okay, and what they would like to hold is a share according to according to Z, right? Not this. So what do they do? Oh, by the way, just I'm putting that there. We have a reconstruction. We know how to reconstruct this, right? And actually here, yeah, so there is some reconstruction metrics you can use, a vector you can use from all the shares even, okay? Okay, so first thing we'll do is that each party takes their share Wi, treats it as a message in the secret sharing scheme Z, and pads it with randomness, does a secret sharing, so it gets a vector, and it sends those shares to, so party I picks this column, it knows it's Wi, and it generates a corresponding column of shares, and then it sends the shares to individual parties, okay, to the other parties, and holds on to one share for itself. Okay, that's the first step. And the second step is then each party, now they are, they're holding something strange, right? These are shares in the Z scheme, but shares of not the original message, shares of these WIs. They'll do something crazy, which is, even though the shares came from the Z scheme, they're going to use a reconstruction of the W scheme on these things, okay? So each party, but it's even crazier, right? Each party is applying the reconstruction not to the shares it got as part of, usually you do reconstruction by multiplying on this side, right? You would take elements from one sharing and combine them. But here we are going to, each party has a row here. So it's going to take its row and multiply it by itself. But of course, it's not silly, because what's going on is it's trying to reconstruct under the hood, it's trying to reconstruct this scheme, W's. So we know R times W is M, or if you write this way, the row W times the column R is M. That is a reconstruction in W. So all this is doing, so what do you get here? Whatever they got, they're going to treat it as their shares of in the Z scheme. But let's see what they're getting here. So if you do R times W here, the top entry is M, and these, trust me, are going to be random elements. Okay, so each of these vectors, they are some random matrix multiplied by this R, random vector multiplied by R, and they're all independent. You get a bunch of independent random elements there. Okay, so the effect of doing R here and getting the Z is exactly taking Z and multiplying it to this product. This product is exactly M and a bunch of random elements. So that is just secret sharing of under the Z scheme. Okay? So this is a simple scheme which lets, because of linearity, switch you from sharing under W to sharing under Z. There was some communication, right? They started with this W, but then the sigmas had to be communicated. Okay, so everybody had to send shares they prepared. Everyone prepared a column and then send it to the other party so that everyone had a row. Okay, so there was communication. everyone talk to everyone. But the computation is pretty simple. You're just doing this linear combination. Okay, yeah, and so now each party will hold a share in the Z scheme. Okay, this was my animation. And now let us go from, so we already knew how to do linear computation, right? If this, what I had earlier where I said the server will take the shares it got and will add, it could have been any linear combination. But what if you want to do some computation which involves linear combinations and multiplication of two inputs, two secrets or two intermediate values. So you have to do linear combinations and there are linear steps, linearly combining variables you have. And also there are, you might once in a while want to define a new variable which is a product of two variables you have, okay? And if you didn't have this, we could have just kept getting shares of all the variables we are interested in by doing linear combinations of their shares locally. But when we want to do multiplication, here is what we will do. We can, and here we are going to use a little more property about Shamir secret-sharing beyond just the fact that it's a linear secret-sharing. So what we'll do is we'll try something else which is also kind of shouldn't have made sense. We take the two shares we got. So I have shares of each, say each party has shares of, so party I, say it has a share of some secret, right? So that is its share FAI, such that F0 is a secret, is some value, let's say M1. And it also has shares of some other secret, let's say M2, right? So this is a Shamir secret-sharing. This is a share in a Shamir secret-sharing of M1. This is an M2. It will do something crazy. It will just say, I'm going to multiply these two values. Okay, so this is a field element, and I've moved to finite fields by now. If you, didn't pay attention, when we did the Shamir secret-sharing, the von Neumann metrics and so forth, we are already talking about finite fields. So finite field is someplace where you can add, multiply, but also divide. You multiply these two elements and call that your new share. Pretend that it's a, Shamir secret-sharing of the product M1, M2. Well, you would be right, so because if I took two shares and took two polynomials evaluated at AI, multiplied it, then what I'm getting is indeed a polynomial evaluated at AI, where the polynomial h is defined as fx times gx. Okay, so it is indeed, it conforms to the Shamir secret-sharing idea that h of 0, h is a polynomial evaluated at 0. It is a product. It's a message M1, M2, and each share is h of AI. The only tricky thing is that the degree of this polynomial is double the degree of the original polynomial. Okay, so it is a different secret-sharing scheme. You might have started with, so the W you originally had a certain size because you had a certain parameters, and now it's a different Shamir secret-sharing scheme because you're choosing a different degree. But they're still both linear secret-sharing schemes, two different linear secret-sharing schemes. And we already saw that you can switch between linear secret-sharing schemes with some communication, and that's what you'll do at this point. Okay, this step is called degree reduction. Going from, so you ended up with, so what do I mean by this? So you automatically got switched into the degree 2t minus 1 secret-sharing scheme. You want to switch back to the degree t minus 1 secret-sharing scheme so that you can continue your computation, and that is done using this communication. And we know that for doing this kind of communication, you do need to rely on number of corrupt parties being smaller than being a minority, and that shows up here. because when you're at this point, when you moved on to this polynomial h for a random variable, if you want to reconstruct that, you need 2D shares. So D is the t minus 1, or the, D was the original degree, now it's 2D. So you need more than 2D shares, 2D plus 1 shares, if you want to reconstruct. Well, you can have that many shares only if there are that many parties. So you need the number of parties to be greater than 2D. Okay. So, and for secrecy, originally you chose this D, such that the number of corrupt parties is less than or equal to D. Okay, so say number of corrupt parties is D, up to D corrupt parties you can tolerate. You want total number of parties to be strictly greater than twice the number of corrupt parties you can tolerate. Okay. So that shows up here. Okay, so I think I will kind of switch gears. So this hopefully, and okay, this is a BGW passive secure protocol. Keeps doing, you write down your function as consisting of linear in a combination of variables and multiplications between variables, and you keep doing, whenever there are linear steps, you just do local computation. Whenever there's a multiplication step, you do this one step of switching, like locally multiply and do the degree reduction, right? And at the end, everybody ends up with the shares of the output, but then you can all talk to each other and get the output if you want. Or whoever needs the output can be sent all the shares. And that's secure against passive corruption of up to strictly less than n by 2 parties. Okay, so just to summarize, so that's one protocol, but we have several protocols by now. I'm not going to actually give you all the several protocols, just the kind of classes of protocols, the two main classes like Kermit was talking about yesterday. So we know that, so what I just now told you is that if you are strictly less than n by 2 corrupt players, so if you're an honest majority, then you have a secure protocol for every, against passive corruption. Okay, but actually you can also get security against active corruption. You need to necessarily reduce your threshold, so you can tolerate only up to n by 3 corrupt parties. Okay? And this is all called BGW protocol. I mean, or that is the first protocol, and since then there are others. And it's uses secret sharing and broadcast. And it's this broadcast part that actually needs n by 3. There are, if you're given broadcasts as a free primitive, you can go all the way to n by 2. There are some technical differences, perfect secrecy, statistical secrecy. I will not worry about that right now. But the main, tool, the only tool essentially is secret sharing. You need broadcast, so, but that's, yeah. And yeah, there is a non-trivial effort in building a broadcast protocol. So if you care about security against active corruption and guaranteed output delivery, then you need the broadcast part. But if you only want security against passive adversary, what I just showing in the previous slide, the only tool there is Shamir Secret-Sharing scheme. Yeah, so no computational hardness is required. Unfortunately, this requirement that you have an honest majority necessitates that you have a large number of parties. Okay? Or at least, maybe you think only one party in the world would be corrupt, but even then you need 3 parties for one party to be a strict minority. Okay? So it's not applicable in a 2-party setting. On the other side, if you don't have honest majority, and in particular something that is applicable also in the 2-party setting, you can still do every function, but now you need something that again Kermit mentioned several times yesterday, something called oblivious transfer or something similar. Okay? We know exactly what kind of things you need to make this go through in some sense. Yeah, so let's say we need oblivious transfer. Okay? And one particular scheme of this kind for passive security in particular is is based on what's called Yau's gobble circuit. Okay? It's a very powerful tool, and it's a special case of what I mentioned earlier, randomized encoding. And another technique, another way to get it is again what Kermit was mentioning yesterday, MPC in the head. And both these approaches only use oblivious transfer. Well, Gauss-Gauss scheme also needs something called pseudo-random function or pseudo-random generator. But yeah, and this one doesn't need anything other than oblivious transfer. There are protocols here. But oblivious transfer itself needs computational hardness or something like that, in the sense if you have a noisy channel or something you can trust to be noisy, you could use that. But the main, the most significant bit here is that oblivious transfer is something that needs assumptions about, let's say, computational hardness. Interestingly, so that's kind of the main two kinds of protocols you would encounter in literature. Honest majority protocols, which typically don't need any computational hardness assumption, and general protocols, which would need some sort of computational hardness or setup. Interestingly, there are also functions which you can do securely without any computational hardness, but also without honest majority. So again, say a number of kind of players. So there are interesting functions, but if you're looking for open problems, here is one. We don't know which ones. Okay, we know we have examples, but we don't know exactly which ones can be done without computational. So in the information theoretic security setting. Okay, yeah, you'd think by now we should have figured this out. We haven't. Have a slide on OT. Okay, so I think that's all kind of I want to say about MPC protocols in general. But since I mentioned OT, and OT showed up several times yesterday, just to demystify it, this is not the most efficient way to get OT, but it's not complicated. It's not hard to imagine getting OT from tools you would be familiar with. So you all know what encryption is, public key encryption. So here is how you can get an OT protocol from a public key encryption scheme with a little more structure. Okay, so OT, the goal was this, right? So the party, say Alice for me, has two messages, X0, X1. Bob has a choice bit B, and Bob should get X0 if the choice bit is 0, X1 if the choice bit is 1, and nothing else. And Alice should learn nothing else about the other string. And Alice should learn nothing about Bob's choice bit. So here is the protocol. This is for passive corruption. So Alice and Bob will follow the protocol. So Alice gets X0, X1, Bob gets B. Bob generates for B equal to, Bob, so I'm calling it, say, let's pretend B equal to 0. So Bob generates a pair, SK0, PK0. It's a secret key, public key pair for public key encryption, using the standard way of generating keys in the public key encryption scheme. He'll also generate a public key, PK1, but this he samples without, goes ahead and samples directly without having any idea of what the secret key is. Okay? And that's a special structure we want in the public key encryption scheme. Not all public key encryption schemes need to have that structure, but many do. And it's not hard to imagine that you can do that, right? Just get a public key, looks like some random element in some set, pick it without knowing what the secret key is. And she sends both these public keys, PK0 and PK1, to Alice. Alice doesn't realize that PK0 is the one for which Bob knows SK0 and the other one is PK1. For her, they're both just two equally valid public keys. She will encrypt message X0 using PK0, message X1 with PK1, and sends both ciphertexts to Bob. And you should see what happens now. Bob can decrypt C0 because he knows SK0, but C1 has been encrypted using a public key about which he has no idea what the secret key is, right? So he has no idea what's X1, but X0 he can get. And this relies on security of the public key encryption scheme. So that's the computational hardness, and with a little more structure. That's the computational hardness you need here. Okay. Yeah. So And in all this, Alice didn't learn anything about B, that even if she's computationally unbounded in this case. We also very much relied on Bob being nice and honest but curious possibly, because if he wanted, he could have sampled both these key pairs so that he knows their secret keys. If he doesn't do that, then he doesn't learn the other string. Okay, so that's all that I wanted to say about MPC, but if you want to use MPC, there are several other issues. If you want to use it in a real life application or in blockchains. So efficiency, scalability kind of questions that we talked about yesterday. Another question which we cryptographers say is not our problem, but it is somebody else's problem, is what is okay to compute and what's not. So MPC tells you if you have some function in mind, and if you have been okay with a trusted party computing it, let's show you how to do it without the trusted party. But maybe computing this function itself is a problem, okay? So that's not a cryptographic problem, it's a problem specific to each application, what functions are okay to compute. For instance, differential privacy is a field which addresses some of these questions. You have to add some noise to functions so that they preserve certain kind of privacy. It's not okay to compute the function without the privacy, right? Not okay in whatever context the application has. So that's, just want to make that point that just because you can do MPC doesn't mean things are secure. It means it's as secure as using the trusted party. If there is a problem using the trusted party itself, then that's a problem. Sometimes in real life, you design your function to allow certain leakage about the inputs, right? Maybe for efficiency reasons, maybe because for utility itself, you need to reveal some information. You can add only so much noise for, say, differential privacy kind of things. So there is some leakage about the inputs. And is it good or bad? That is a separate question. Another thing is the network model. We have a fairly simplistic model. Everyone talks to everyone else. The set of participants are known ahead of time. Everyone has, the other party's a direct channel to the other party. And everyone comes online and willing to talk to each other, right? So, but all these assumptions are, in some setting like blockchains, they don't quite translate to the same model we have. Or asynchronous communication. So there is a lot of literature on getting secure multi-party computation when there is no guarantee on network delays, right, how long it will take. But those protocols would give you only, they're very pessimistic about the network model, that there is no guarantee on, eventually messages will be delivered, but you have no idea how long it will take. So eventually your computation will finish. But say if you're in a practical application or using some blockchain or something, you wouldn't want to just wait forever. You might want to time out, and so maybe some communication is faster than other communication. Some channels are faster than others. How to there are all these systems issues of when to time out, who should time out. So they're all kind of separate questions you will need to handle, potentially need to handle in systems settings. Okay, let me now just mention a few things without getting into details. PIR is a very influential notion in theory, and maybe in practice in future also. What is PIR? What's the notion? So there is some database, and there is some client who wants to retrieve an element from the database. The database is just a vector, and what the client wants to retrieve is just some value in the ith position in the vector. And the only privacy requirement is that the server should not learn which coordinate the client is retrieving. There's a trivial solution for this. The server could send the entire vector, the database, to the client, and the client can locally pick up whatever it wanted. And the question is, how much better can we do, right, than that? And to be able to do that, say if you don't want to make computational assumptions, you might want to relax from having one server to multiple servers. Okay, so there's a whole field of literature on PIR. Oblivious RAM is another, this kind of, you have data in the cloud storage, you want to work with it. But now you want to also, you have blocks of data in the cloud. You want to, all the data you can imagine is kept encrypted somehow. The cloud doesn't know what the data is. But you want to go and read and write the data. Sure, that by itself is not a problem. You go, fetch data, decrypt it, do whatever you want, send it back. Well, the problem is, first of all, you don't want to reveal which pieces you are fetching. But also, more critically, you don't want to reveal. So there's one database sitting there, and you're doing many operations, read and write, and you don't want to reveal your access pattern. So you might have written something, you want to read back that thing. You don't want the server to realize that you're reading back what you just now wrote. Okay? So kind of more complicated problem, and solutions are more complicated or less efficient. But there are very non-trivial things you can do. Finally, there's also a problem or an area called searchable encryption. It's defined trying to be a little more pragmatic. So these are kind of coming from from a more theoretical point of view, where you don't want to reveal anything to the server. In this case, no access pattern should be revealed. In searchable encryption, you're okay with, you describe as part of your problem statement, it's okay for the server to learn something. What thing? It can reveal, it's okay to reveal the access pattern. In the sense, if I'm searching for the same keywords, or if I'm retrieving the same documents, I'm okay with the server learning that information. But I don't want the server to learn what the keywords are, or even how many documents I have. Only when I retrieve them should the server see that. Okay, so the searchable encryption, the question is, say Gmail, you have put all your encrypted email with Google. You want to search on your email. You cannot just go and bring all the email and search locally. So you want to give the keyword query to Google. You don't want Google to learn what's in your keyword. You don't want Google to know what's in your email. And how do you do it? So you can, again, do very non-trivial, useful things there. But all these, you can hope to improve. Well, oblivious RAM, in some sense, we know optimality. Okay, so, I have time till, till 20. Okay. Yeah. So, switch gears again and mention another topic called homomorphic encryption. I realize that I don't have my animations here. So what is homomorphic encryption? And I'll start with the kind of more basic notion of homomorphism, and then we'll talk about fully homomorphic encryption. So homomorphism refers to this property of a function that's mapping between two groups. So say there are two groups, G and G prime. So group is where you can do addition, essentially. And we say the function is homomorphic if this kind of commutativity holds, in the sense you could first compute the function f in the say group G, the first group, and then that moves you to group G prime, and then do the addition there. Or you can first do the addition in group G and then move to group G prime. Okay? And both these should give you the same value. That's when you call f a homomorphic function. So what is homomorphic encryption? I would have probably preferred the word homomorphic decryption, except decryption is not the utility you're talking about. So basically, homomorphic decryption says the two spaces we are talking about are the messages live in a group. That's a message space. And the ciphertext them also form a group, okay? Or the ciphertext space. And the decryption operation, which maps, without loss of generality, let's say it's a deterministic operation. The decryption function is a homomorphism between the message space and the ciphertext space. So ignoring things like errors in decryption and so forth that you may be okay with, this is what it says. You decrypt a ciphertext, get a message, and decrypt another ciphertext, get its message, add the two messages in the message space. You could have obtained the same thing by doing some addition operation in the ciphertext space. So it's not something you're used to typically, right? Ciphertexts are useless chunks of random looking strings, but if there is some group structure in that space, you add your ciphertext and then do the decryption. You should get the same result. Okay, so that's exactly what this says here. So the decryption operation is a homomorphism between the message space and ciphertext space. It's probably more useful to think of in terms of encryption being homomorphic, except encryption is a randomized operation, so it's not a not a function, right? So, but if you forget that, basically what we are saying is that you can get the effect of, you can take two ciphertexts encrypting X and Y and do this magical operation in the ciphertext space, and you would have ended up with a ciphertext of the sum of the two messages. So you have the ability to add messages under the wrap of an encryption scheme without ever being able to decrypt, figure out what you managed to add, right? So that's, of course, you can always do it, if you have the decryption key, you can do this. But the interesting question is to be able to do this operation, to be able to define this addition in the ciphertext space in a way that doesn't violate the secrecy of the encryption. Okay? And there are many examples. Actually, I have many more, a few more in the next slide. But I'll start with this one. This is called El-Gamal encryption. If you've seen Diffie-Hellman key exchange, it's essentially that. So the public key is, so in Diffie-Hellman key exchange, two parties, one party sends G to the X, the other party sends G to the Y, where you think of exponentiation. The inverting exponentiation is a hard problem. The discrete logarithm is a hard problem. So the message that the receiver sends in Diffie-Hellman key exchange, think of that as a public key. Okay, so I called it capital Y here. So that's a public key. The secret key is a little y. The receiver holds on to that. And to encrypt a message using this public key, you pick some randomness. So encryption is a randomized process. What is a randomness? It's a little x. It's some exponent for the whatever group you're working on. And the ciphertext is this, G to the X, which would have been one message in the Diffie-Hellman key exchange, and M times capital Y to the X. This capital Y to the X would be the key in Diffie-Hellman key exchange. This is G to the XY. So there are two ways to compute this. One is as Y to the X, that's what the sender did. And the receiver, who knows little y and who is given G to the X as part of the encryption, can also compute G to the XY, right? So that's El-Gamal encryption scheme. And it has a homomorphic property where I define the operation in the ciphertext space as follows. So you just multiply coordinate-wise the group elements. So G to the X1 times G to the X2 gives you G to the X1 plus X2. So let's call that X3. And so this is a group where multiplication is the operation. M1 times Y to the X1 and M2 times Y to the X2 is the same Y, gives you M1, M2, Y to the X1 plus X2, which is X3. Right? So this is a valid ciphertext using randomness X3 for the message M1, M2. So from two ciphertexts for message M1 and M2, you can multiply them and get the message and get a ciphertext for M1, M2. Okay? So that's an example of a homomorphic encryption. There are more examples. Why do we need more examples? For encryption, so if you get a good encryption scheme, you might be okay with just that, like El-Gamal encryption, or say some variant of that, which has sufficient security properties. For your browser or internet communication, you're happy with just one encryption scheme. Use different ones because different people have, different efficiency and security trade-offs. But with homomorphic encryption, you might need different encryption schemes for another reason. The group, the message space and the message space, the group, that is a message, is determined by the encryption scheme. Whereas if you are trying to use this homomorphic encryption for some application, your application decides where the message comes from and what is the group operation you want to do. Do you want to do XOR of bit strings? Do you want to do addition modulo 100? There are two different things, right? So you cannot just let your encryption scheme decide what group operation you would be happy with. That comes from your application. So you want to map your applications group somehow into the encryption schemes group, and it'll help if you're, it's not possible typically with just one encryption scheme. So we have several things in the literature that are useful. Elgamal we already saw. Elgamal, the group is some group where what's called the decision Diffie-Hellman assumption holds. There are many examples in elliptic curve cryptography. There are elliptic curve based groups. You also have number theoretic groups, so something working modulo an appropriate prime, and working with quadratic residues, whatever that means. So that's one kind of group, working modulo prime in some sense. There's another very old, one of the oldest, I guess, encryption schemes by Goldwasser and Micali based on quadratic residuosity. So the computational assumption here is different. And there the message space is bits or bit strings, right? And there's another one, PIA encryption scheme, where the message space is addition modulo an integer. The integer has to have some structure, but typically you're okay by choosing it. This is very useful because often what you want to do is add integers. So just pick your large enough n so that you'll never have things overflowing, and this is what is useful in many applications. There's a variant of there is a kind of a PIA++, a fancy version called Damgard-Urich crypto system, where it's a family of encryption schemes. So it's not, for each value of s equal to 1, 2, 3, you can have your message space being Zn to the power s, okay? So the addition is modulo n to the power s, and that's a message space. The ciphertext space is a subset of Zn to the s plus 1, okay? So for s equal to 1, that's the same kind of thing PIA has, but now you can, you have the ladder of groups, and you can start with your messages at, say, the bottom level. If you do encryption, you go to the next level. And suppose for some reason, and then you can do computation at that level. It's homomorphically applies to the message and the level below. But for some reason, suppose you end up encrypting the ciphertext again, then you go to the next level. And then you don't directly compute on the original message, but you can still compute on the ciphertext at the level below. Okay, so you might wonder why you would want to do something like this. There's a very nice application which looks tailor-made for Damgard-Urich, or for which Damgard-Urich looks tailor-made. And that is a PIR application, okay, private information retrieval. But there's a computational setting. There's only one server. And my database, the vector I have, has integer values in them. Okay? So integers in some small enough range. And I'm going to use homomorphic encryption, PIA encryption, Damgard-Urich encryption maybe, with a sufficiently large modulus. So here is what we can do. I'll try to do some animation to explain this. So I put a value in a colored box to indicate it's a ciphertext. So the actual message is X. It's in the colored box because it's encrypted. And there is this magical operation, the homomorphic operation in the ciphertext space, that can take two ciphertexts and give you a ciphertext which has the sum of the underlying messages. Okay? So that is what PIA gives you. It also automatically gives you one more operation, which is I can take an integer in the clear, and I can take a ciphertext of y and get 8 times y. You can do this just by addition, right? You can kind of do repeated doubling or repeated addition to go from, and so the 0 star, so I'm going to use the term star. So 0 star C, C being some ciphertext, is just, think of it as encryption of 0. 1 star C is just C itself, but you want to define, and you can recursively define A plus B star C as A star C plus B star C, right? So if you have this addition, you can also kind of get for free addition by plain text, multiplication by plain text. What you don't get is multiplication between two ciphertext. So let me try to illustrate this. So here's one approach. Here's the first thing you could try to come up with. So here's a database, x1 to xn. Here is a client holding the index I. They want to pick up xi. And what the client would do is create encryptions of zeros and ones, a vector, where the ith position has 1, everywhere else there is a 0. And sends it to the server, and the server will do this star operation, will get new ciphertext, and these are all going to be zeros, and this is going to be, so it's important, these are the clear text, x1 to xn. Okay, so server can do whatever it wants, number of times to add and so forth, depends on the plain text. This is under the wrap, it's inside the box. So the server has no idea that it's actually adding a bunch of zeros and getting a 0 here, right? So it doesn't know what these values are, but in the ith position, what it will get is xi, okay? And that's still too much to communicate, as bad as sending the whole database, but here is where you can use, here is where you'll get some saving. You can add all this up, and that will be just summation of ciphertext of xi, send it, the client can decrypt, okay? So there's some saving, not the best you can hope for. Client is still communicating a lot, but the server is sending very little. To get something more, balanced and pretty good, we'll use Damgard-Yurik. So you put all your entire database into this tree, at the leaves of the tree, let's say, and divide it into two halves, right? The left half, right half. And say the client wants to pick up some value here, let's say, I don't know where it'll be, sorry, here somewhere. So the first half it doesn't care about. It wants to look into the second half. So it'll create two ciphertexts. The first half is 0, the second half is 1. The server will take this 0 and use each of these plain texts to do the star operation. So it'll end up with a bunch of zeros here. And use the plain text here, do the star operations on this ciphertext. It'll get exactly the same values here, right? The same value, sorry, it'll get these values now inside an encryption. And then there's still no compression has happened. You just add them, point by point, point to point, I guess, and reduce it by half. So the zeros are adding to these guys, you'll get the same value here, right? So what we have managed to do so far is these values are now inside a ciphertext, unfortunately, I guess, but they are only the relevant half is in the ciphertext. To continue this, the client would also send, say it's interested in like something in this quarter of the data. So at the next level, again, it wants to go to the right? So it'll have, again, a 0, 1, but now this is encrypted using the next level, where these things are the plain text, and this is a ciphertext. So now, even though they are colored, think of them as plain text. So we'll do exactly the same thing, multiply this, fold them together, and now it has these ciphertexts, sitting here under the next layer of encryption. You can keep doing this, and you'll get a single ciphertext at the end, which the client can decrypt all the way back to the original clear text and get the message. Okay, so it works. That's all I wanted to say. So this gets you a logarithmic communication. So n is the size of the database. Both server and client are sending logarithmic communication. This may be not the best time to start on fully homomorphic encryption scheme because I have 30 seconds. Should I take 5 minutes or? Okay, so I'll try to, I just have two kind of sketchy slides on one. So homomorphic encryption lets you do a group operation in some group of the scheme's choice. But if you want to do addition, if you want to do full-fledged computation, say over bit strings, you want to do addition, say XOR, and multiplication, which is AND. Or you want to do something like NAND, which is a complete operation. So you want to do, essentially move to a ring instead of a group, right? So, okay, so what we are going to use, so we'll see a sketch of, it's something that has happened in the last decade or so. Several very, clever schemes have come out of nowhere to do fully homomorphic encryption. Okay? And a lot of that has, the more recent ones use this assumption called learning with errors. It's in the family of what are called what's called lattice cryptography. So let me start with, this is not the statement of the assumption, but there's a consequence we need. So the consequence is that there's a way for you to pick a pseudo-random matrix M. So this matrix looks random to someone, but you have some additional trapdoor knowledge about this matrix, which will let you find this vector Z, such that M times Z will give you a vector with small values. So this E, think of it as an error vector. So if you came up with a matrix M such that M times Z equal to 0, then everyone can figure this out. They can do some linear algebra and figure out that the rank of this matrix is, well, in fact, rank of this matrix is not full, and they can always find the Z themselves. But what you're trying to do is not say M times Z equal to 0, but something with very small entries. Okay? Think of these are all numbers modulo some very large number. Being small means it's close to 0, plus minus. If you know what LW is, this is what is internally going on. You can pick A and E and S a priori and appropriate distributions and solve for B. Okay, but doesn't matter for us. This what it is. So two things. This looks like a truly random matrix to others, but the secret matrix vector Z that can almost kill this matrix, right? Give you some short, small value vector. And here is an encryption scheme. This generates a high waters. So it's very simple. So to encrypt a bit, so it supports bits. Okay, to encrypt a bit mu, you pick a random matrix R, and your ciphertext is M times R. Well, I'm going to ignore it's M transpose. So I'll just call it MR plus either MR or MR plus G, where G is some matrix I'll tell you in a bit, depending on whether mu equal to 0 or 1. Right? So it's either MR or MR plus G. So the ciphertext is a matrix. You're encrypting a bit, you get a matrix. And why is this hiding whether this G is there or not? That's because for somebody who doesn't know the trapdoor, this M looks like truly random. And if M is truly random, this MR, the parameters are such that this MR is truly random. Okay, so there is no information. If M were truly random, there is no information in the ciphertext about mu. So computationally, it's as good as that. How do you decrypt? You multiply this ciphertext with your Z. Okay, so it's M transpose. So I'm multiplying by Z transpose on the left. So C, the ciphertext C is this quantity. When I multiply it by Z, you get ZMR plus mu G. ZM is just E. So it's basically ER plus mu Z mu G. Okay, so this quantity is designed to be small. Why? Because E is small. This quantity becomes a little bigger than E, right? Because you're not looking at E times R. So there are number of rows of R shows up as a additional factor, but it's still small. If you pick your parameters, so it is still small. And there is this thing, and this is a large value. So G is such that this ZG, if it is there, it's not close to 0. There are entries there that are far from 0. So by looking at, if you have Z, you compute this and check if it is all close to 0 or if it's not close to 0. And that's how you decrypt, okay? Okay, but the new thing, the novelty is that you can do computation, and we'll do NAND. It's basically, addition is easy to see, it's a multiplication that's hard. But the NAND here looks like this. So G minus C1 times BC2. So G is a matrix, C1 is a matrix. What is BC2? It takes a ciphertext C2, and which is already a matrix, gives you a bigger matrix. And it's doing something called bit decomposition. So there are large values. Ciphertext looks random, right? It has very large values in there, integer values. And BC2 blows it up. Each integer is now written as a bit string. It's bit representation. So the matrix becomes larger, but each entry becomes a bit. G is basically NAND is doing 1 minus AND. Okay, the G is a valid ciphertext of for mu by taking r equal to 0. So you think of G as ciphertext of 1, not the random ciphertext, but works like a ciphertext of 1. What's main thing is that this is where the action is. This looks like AND. This has the effect of the ciphertext of AND of C1 and C2. So why is that? So for that, I need to tell you what G is. G is so bit decomposition is not a linear operation, but converting it from bits back to an integer is a linear operation. You multiply it by these, 2 to the 0, 2 to the 1, 2 square, and so forth. So you can take a bit representation and multiply it by some vector, get back an integer. You do that for every vector that's showing up here. That corresponds to a matrix, and that's what G is. So now, if you look at just this quantity C1, BC2, I would like to say that is an encryption of M1 times M2, where M1 and M2 are the messages in C1 and C2. What I mean by that is if I decrypt, or what I'm going to check is that if I decrypt, will I get back M1 times M2, or mu1 times mu2. I think we are too close to lunch, so trust me, when you do this, it becomes just 2 lines, you can verify yourself. What you'll be left with something mu1 times mu2 ZG, which is a part you actually want from an encryption of mu1, mu2, plus something. And this noise does take some hit, it does blow up, but the whole point of doing bit decomposition is to keep that noise, that error still small. It's not that small, but it's not too large, it gets multiplied. So there's a limit on how many times you can do that. That's a very basic FHE scheme. This is not the most efficient one. There are much fancier ones, and using stronger assumptions also. Okay. Okay, but I think I'll wrap up with that. Just a reminder that we have several things out there in cryptography that you could use. A lot of them are, a lot of things that could potentially be directly used in blockchain kind of settings are in the multi-party computation basket. But there are other interesting things also that you could potentially use. And I would, homomorphic encryption and so forth. So this tends to be more interactive. Things in the homomorphic encryption world are less interactive. It's a one-shot kind of thing. So that's probably more suitable for certain application. Okay, so I'll stop with that.
Okay, that's a wonderful overview.